10.5 is going to explore additional aspects of logarithms. Now, up until this point, we've been talking about log base 10, or the common log. And what we are going to talk about now is something called the natural log, and that's abbreviation is ln. We're going to talk about how it relates to base E. So we're going to look at a little example for a minute. So we talked about compound interest. So if you're earning interest on money you've invested, or if you are paying interest on something you've purchased, interest, the final amount, A, is equal to the principal, the initial cost of the item, times 1, so that's the whole, you pay on the whole value, plus R, the interest rate is a decimal, divided by the number of times the interest is compounded to the exponent nt. So it seems like a lot of variables. But when you look at a table, we're going to invest $1 for 1 year at a rate of 100%. So our P, our principal, is 1. Our rate is 1, because if you think about 100% as a decimal, it's just 1. And time is 1, because it's 1 year. So we're going to put them into an equation, into our equations right here. And it'll simplify down to this. So n is what we are going to change in this problem. Okay? N is the number of times the interest is going to compound per year. So if it's just going to compound once, one time, this would be our equation. So we really would be looking at 2 to the first, and you would get $2 at the end of the year. Semi-annually, so twice during the year, so 1.5 squared, you'd actually get $2.25 at the end of the year. Quarterly, so if it compounds 4 times, 1.25 to the 4th power, substituting n equals 4 into this equation, we would get $2.44 and some decimal. Now if it's going to compound monthly, that means n is 12, so that means I have 1 plus 1 over 12 to the 12th power. And when you put that into your calculator, you get 2.6130 some long decimal. If it compounds weekly, there are 52 weeks in a year, so now my equation becomes 1 over 52 to the 52nd power, but I end up with 2.6925. So even though it's compounding a lot more, more frequently with 52 weeks compared to 12, this 1/52nd is really only going to change it by about 8 cents. Daily, if we just go to a standard year of 365 days, 1 plus 1 over 365 to the 365th power, we do that, we end up with 2.7146. So you can see my growth is starting to slow, which is what we expect in exponential functions. At some point, things are going to go asymptotic. Hourly, if you are curious, 365 days in a year times 24 hours is 8,765 hours in a year. 1 plus 1 over 8765 to the 8765. And while you might think that's a ginormous number, it's actually going to end up being 2.7181. Every minute will be 2.7182. Every second, 2.7182. And you see that we have leveled off right in this range. What's special about where this levels off and where it really quits growing for all intent and purposes, if n continued to increase even larger, compounded continuously, the dollar value would approach the number E, which is this non-repeating decimal. It's the second, try this again, second most common irrational number next to our favorite, which is pi. Remember, irrational numbers are non-repeating decimals. So, the number e is referred to as a natural number e. So an exponential function with e as your growth factor is known as your natural exponential function. So the natural log which I said earlier is ln, is a logarithm with base b being the number e. So here's kind of our conversion. Log base e of x equals ln of x. Now remember, common log base 10 of 10 is 1, and exponentially 10 to the first is 10. When we're talking natural log, we're talking that the ln of e is going to be 1, or e to the ln is 1. They're opposite operations. Okay, so the natural number e and the natural log undo each other. So the same strategies we used about raising things to the common log or base 5 of 5, we're going to use with e and natural log. Those two are separate buttons on your calculator. Log and ln are not the same. So approximate these to 4 decimal places, which basically means go to your calculators. And e to the 0.5, when you go to your calculator, is going to be 1.649. Now remember, what does that mean? That means that the ln of 1.649 is 0.5. Remember that exponent form and log form, those rules are still applying. So e to the negative 8 is 0.0034. Okay, or as your calculator, 3.355 times 10 to the negative 4th. I have a little bit of a rounding difference there based on when I did it, but remember, if it says that e to the negative 4, that scientific notation, remember to move your decimal point. The natural log of 3 is 1.099. Remember, that means e to the 1.099 power is going to be 3. The natural log of 1/4 is negative 1.3863. So that's straight calculator work. Write the equivalent expressions in exponential or log. So now we're going to move back and forth between our forms. So e to the x equals 23. That's the same thing as saying the natural log of 23 is x. E to the x equals 6. That's the same thing as saying the natural log of 6 is x. We're getting that variable out of the exponent position so we can go to our calculator or a table and solve. Natural log of x equals 1.2, etc. We can't solve that, but we can put it in exponential form and say e to the 1.2528 power is x. The same way here, we can say e to the 2.25 power is x. So that's how we can move between those two forms to get that variable out where we can solve for it. If we need to evaluate e to an ln power, these are opposite operations. They are going to cancel. The answer is 21. Ln of e to a power, those are going to cancel, and we are left with x plus 3. Okay, so the other way you could more formally think about this, our exponent rule is that the exponent comes out front, and I have ln e to really the first power. This becomes 1, and so that's why we're left with this. It doesn't just magically disappear. There is math behind it. Conversely, e to the ln of 7 is just going to be 7, and the ln of e to the 5x minus 7 is 5x minus 7. This is the same rule as when we take log base 10 of 10 to the 5th, we say is 5. Okay, so that's the same rule in effect here that we were using with the common logs. So when we go to solve, we are still working with our isolate the variable. Okay, get the variable by itself. It's in the exponent position, and so what we're going to be doing is we're either going to be taking the natural log of both sides, or we're going to be taking the e, raising everything to a power of e to solve. So here's what it looks like. So first, we always isolate the variable. So get everything you can away from the variable, and then you're either going to use e or ln to solve the opposite operation. So here, we're first going to subtract 4 from both sides. So I have 3e to the negative 2x equals 6. Now I'm going to divide both sides by 3. So I have e to the negative 2x equals 2. So I can't simplify that anymore. So now, to undo e, I'm going to go ahead and take the natural log of both sides. Because what I do to one side, I can do to the other. Exponent rule, opposite operations, however you want to think about it. 2x equals the natural log of 2. Divide by negative 2. And x, go to your calculator, ends up being negative 0.3466. So much the same process that we saw with the common log solving. So if I go ahead and look at this next problem, very similar. I'm going to subtract 5 from both sides, divide by 2. Now to undo e, I'm going to go ahead and take the natural log of both sides, because I'm going to do the opposite operation of the natural number e by taking the log. That's going to give me negative 2x is equal to the natural log of 5. Divide both sides by negative 2. Go ahead to your calculator, and you end up with negative 0.8047. Go ahead and tune into part 2 for the last 2 examples.